I am Professor Antonio S. Marajas, and this is Computer Applications in Industry. Okay, so let's have an example. No? So what we have here is a Boolean expression, and we want to obtain the Siemens equivalent or the Siemens programming equivalent of this particular equation. No? So the first step is for us to make a logic gate equivalent or logic circuit equivalent of the equation. So you have AB here. We know that we can represent this with an AND gate. Okay, we have inputs A, B. Then we have here another AND gate, which is represented by B, C. Okay. Two AND gates are being ORed together. Okay. And the output is X. Okay. So that is our logic circuit equivalent of this particular equation. So how do we make a program, or how do we represent this in our Siemens ladder equivalent? Now, we know that this AND gate here, two input AND gate, can be represented by normally open contact, which is connected in series. Okay, let's say this is your A can be represented by, for example, A here is I 0.1, B is I 0.2, C is I 0.3. So you have only A, B, and C. So this one here is I 0.1, and this one here is I 0.2. Okay, and this two AND gates are being ORed together. So in other words, BC here will be written in this particular area. Okay, then they are being ORed together. This one here and this one here are being ORed, so they should be connected in parallel, because OR gate means parallel connection. So this one here, it becomes what? This is your B again. B is represented by I 0.2 and C is I 0.3. Okay? And then you have here output Q 0.0, which is actually your X. Okay? So that will be your Siemens equivalent for this particular equation. Okay? So again, you have an AND gate, two input AND gate. So you have two contacts connected in series. Another AND gate, two contacts connected in series, and they are ORed together, meaning to say they are connected in parallel. Okay? So that your output Q 0.0 is your X here. That is for number 1. How about number 2? So you have A plus B complement times C plus D complement is equal to X. Again, same representation. So if we will draw the logical circuit equivalent, this will be an OR gate. Okay, so this is your A, and B here is complemented. Okay, then another OR gate, then C, and then your D here is complemented, and the output of CD and C plus D bar and A plus B bar are being multiplied together. So these two terms are being multiplied together to produce an output X. So this is your C and this is your D. Okay? So that is your logical circuit equivalent. So how do we draw the Siemens equivalent for this? So you have OR gate. Okay? In other words, OR gate is represented by what? Parallel connection. Okay? So your A is parallel to B complement. So you have here B complement, meaning to say that when you say B complement, that will be normally closed contact. That will be the representation of your complement here. That is, if complement is, or the inverter is placed at the input part of your circuit. Okay? So you have A and B, and they are parallel together. Okay? And then it is being, the other parallel connection is being AND or series connection. So this one here is parallel again. You have, they are connected in series, so you have parallel connection again. You have C. Okay, so this is your A, which is I 0.1, and this is your B, which is I 0.2, and let's say C is I 0.3, and then the other one, okay, this is your D, which is normally closed, and then you have final output X, that is Q 0.0. So that will be your representation, no? So you have this one here, parallel connection. So you have I 0.1 and I 0.2 for A and B. And then another parallel connection, which is C and D. Okay? This one here is I 0.4, for example, for B. And these two parallel connections are being connected in series. Okay? Okay, then you have output Q 0.0 as your representation of X. So we have here an example. Now if you notice that most of the variable terms here are complemented. Okay? Now, if we will draw the logical circuit equivalent of this one here, then it will be very easy for us to draw this one. But once the logical circuit are to be converted into Siemens, then we will have a complication because of the inverters. Okay? So what we will do is to use the Morgan's theorem. So ato sa ni siya bungkagon. Okay? Then we will obtain the logical circuit equivalent, then the Siemens equivalent. That is the easiest way on how these logical circuits can be represented in ladder diagram programming using Siemens. Okay? So, for example, this one here, A plus B complement can be complemented or can be, what do you call this? Demorganized by representing A plus B complement here with A. The plus sign here is changed to multiplication sign, B, and each of the variables are complemented. That is the De Morgan's theorem. Okay? Then, here, if you notice that AB plus BC complement is also complemented, so ato sa siya bungkagon, ganing natin sa gawas nga complement. So this becomes what? This becomes AB bar, okay? Then this one here is changed to multiplication sign. Then you have BC complement, and then since nga ito naman na siya demorganize, mahimo na siyang double complement because the sign here is already changed to from addition sign to multiplication sign. Okay? So is equal to X, then complement. Okay? Then this becomes what? A bar, B bar times, this one here is to be complemented again. So this becomes what? So let's make another parenthesis. So this becomes A bar plus the sign here, which is multiplication sign, is changed to addition sign. So you have B bar, okay? Then times BC complement, that is rule number 9, I think. Double complement is eliminated. So you have BC, okay? And then all of these are being complemented. That is equal to X. Okay? So this one here can now be represented in your logical circuit. So you have this one here is AND gate. Okay? You have A bar, B bar. Then it is multiplied to these variables here, or variable terms. So you have, okay, so you can remove this one here actually. This one, you can remove that. Okay, so you have no, this is an OR gate. So this will be represented by an OR gate. Okay, now A bar, B bar, and then multiply it again to another AND gate, BC. Okay, and all of these are being multiplied together, so you will use AND gate. Okay, then the AND gate is inverted, so you have an inverter there. Then this is equal to your X. So this is your BC. So this is our logical circuit equivalent. So how do we obtain the Siemens equivalent? Okay, so how do we obtain the Siemens equivalent? So again, you have here an AND gate. So you have two normally closed contact. Why normally closed? Because it is inverted. So you have A, then you have B in series connected. Okay. Then you have an OR, and all of these are being multiplied together using AND gate. So series ang iyang connection, no? So you have again another representation, which is your A bar, okay, and then it is parallel to B bar, okay, that is this one, and then it is being multiplied to BC. So you have series connection, B, C, okay. Now take note that it is also being inverted. So this is now how you will use your, what you call the inverter Siemens equivalent. So this one here, you will have Q 0.0, that is for your relay. Okay, this becomes your network 1. Okay, so again, let us represent A with I 0.1. This is I 0.2. Then A again, I 0.1. And B again, I 0.2. And B again, I 0.2. And C, I 0.3. Okay? And then, we're not yet done with our inverter here. So this belongs to network 1. So we will now add our inverter. That is now under network 2. Okay? So what is network 2? So you have a normally closed contact, okay, for your inverter. And then this becomes your Q 0.0. And then the final output Q 0.1, and that is your X. Okay? So Q 0.1 is actually your X. Okay? Your Q 0.0 is your logic relay with an internal contact of Q 0.0, and then the final output is Q 0.1. So that is how we make a program using ladder diagram in Siemens. I hope that you understand. So again, just a review. How do we obtain the Siemens equivalent? So this one here is AND gate. Okay, series connection, normally closed contact because it is inverted. Okay, the inputs are inverted. And then you have an OR gate. Okay, meaning to say parallel, and both inputs again are inverted. Okay, then you have DC, an AND gate again. Okay, so why is this our connection? Because it is being AND, meaning to say they are connected in series. Okay, each are connected in series. And then since we are having an inverter, so the final output Q becomes your LR for this network 1. Okay, that is your LR. And then you have here your LR interconnection or internal connection, which is represented by Q 0.0 here. Okay, and then your final output X here is represented by Q 0.1. So this one here, this portion here is actually the equivalent of the inverter.